To test the effect that a categorical independent variable has on a quantitative dependent variable, the two-sample t-test may be used. Recall from a previous video that the grouping tool may be used to group quantitative data by independent variable category. We then can compare the sample means. The difference between sample means is then compared to an assumed difference of 0. That would be the null hypothesis for our two-sample t-test. Rejecting the null allows us to conclude that there is a true population mean difference. In other words, we would conclude that the independent variable does have a significant effect on the dependent variable. We can see here two samples of spending, one for the men and one for the women. We calculated previously the sample mean difference of $775.63, but we had no way to determine if that difference was statistically significant. The two-sample t assumes 0 difference for our null hypothesis. Rejecting that null hypothesis allows us to conclude that the difference between the means is statistically significant. We could easily run a two-sample t-test using our Excel tool Testing and Estimation. First, we would need to input our independent or grouping variable. Here that's variable number 4 for gender. Remember, when we input a categorical variable, we must also input the category labels for that variable, here F and M. Our dependent variable is number 3 for spending. The Worksheet tab 2 t-test has our results. To run our two-sample t-test to consider the effect of gender on average amount charged, we would begin with the familiar step 1, formulating null and alternative hypotheses. Here our null is simply that mu1 equals mu2. In other words, the difference between the means is 0. Next, our sample mean difference of $775.63 is compared statistically to that assumed difference of 0. Our results here are notable and highly significant. Please note also the 92 degrees of freedom being used for our two-sample t-test. This comes from what is known as the Satterthwaite approximation and calculated by our statistical software. So our results, t for 92 degrees of freedom, is a very strong 4.41 with a p-value very close to 0. Like any procedure using quantitative data, outliers can have an effect on our results. The sample data, therefore, need to be checked for strong skew and outliers, and the grouping tool may be used. Recall also that all t procedures assume normal population distributions, and here we have to check two assumptions of normal distributions, one for the men and one for the women. Our results from the grouping tool show approximately normal distributions, and neither has any strong skew or outliers according to the z-scores. Let's go to our Excel tool now to practice using our two-sample t-test. We're testing the effect of gender, which is variable number 4, on spending, which is variable number 3. The results are on the Worksheet tab 2T test. First, our null hypothesis. Here we're assuming 0 difference between the population means. In other words, we're assuming that the population of all men who have the credit card and the population of all women who have the credit card, two separate populations, spend the same. Mu1 minus mu2 is 0. And we observe the sample mean difference. Here we could see that the sample mean for men, a little bit more than 36.95, minus the 44.70 and 82 cents for the women, gives us a negative difference of 775.63. It doesn't matter what we make sample 1 or sample 2. That is, the amount of difference won't be affected, only the sign. So we would either conclude that the women spent more than the men, or the men spent less than the women, which is the same conclusion. We could easily change that order on our data sheet. And now we see a positive difference. The same amount, however. So our results, T for 92 degrees of freedom, is a very strong 4.41, which means that our sample mean difference is 4.41 standard errors above zero. The probability of getting that much difference at random, if we assume no difference in the population means, is very close to zero. Therefore, this is a highly significant difference. We could estimate at 95% confidence that the true mean difference is somewhere in the range 426.59 up to 1124.67. The best technique for comparing more than two means is the one-way analysis of variance, or ANOVA. ANOVA allows us to test the significance of mean difference when quantitative data, our dependent variable, are grouped by independent variable category. Though mathematically quite different, the ANOVA test is conceptually no different than the two-sample T, except that we can compare more than two groups in the same test. The ANOVA procedure uses the F-test to determine statistical significance. Our F-test statistic is calculated as the estimate of difference between the sample means divided by our estimate of variability within the samples. Some of our differences can be positive or negative, and therefore our total measure of difference is based on sum of squares. So our numbers look a little bit different. But once we calculate a single F statistic, we could then obtain a p-value and make a decision about our null hypothesis. When F is large, the results tend to be statistically significant. Because it's based on squares, when our F statistic increases, the p-value will decrease. In other words, when F is large, there is a lot of mean difference relative to variability within our samples. We can easily run a one-way analysis of variance using our Testing and Estimation Excel tool. We simply input an independent variable and dependent variable number. Because our independent variable is categorical in this case, we must also input category labels for our IV. The Worksheet tab ANOVA has our results. ANOVA always has the same null hypothesis, that is, equal population means, or no difference. If we reject that null hypothesis, we would conclude alternatively that there's some difference between the population means. Does education level have a statistically significant effect on average amount charged? To answer this question, the amount charged data are first grouped into three samples, one for the BAs, Ms, and Ds. We could observe the sample mean difference between these groups, but the ANOVA method will use the F-test to determine if this difference is statistically significant. Below, the results show no significant difference in the average spending between the three groups, and we could see the very high p-value over 20%. Therefore, our null is not rejected. We also see group mean confidence intervals, and we could see further significant overlap or common range, which often indicates no significant difference between those groups. Our ANOVA method has two required assumptions: normal population distributions and equal variance. The assumption of normal distributions may be checked using our grouping tool, when the data can also be screened for any possible outliers. The assumption of equal variance may be tested using what's called the 2 times rule, simply by comparing the largest standard deviation to the smallest standard deviation. If the largest group standard deviation is not more than 2 times the smallest, we could assume no statistically significant differences between the variances. In other words, we could assume equal variance. Looking at these results, we could see that though the ANOVA produced no statistically significant effects, the data are appropriate for the use of the ANOVA technique. Let's go to our Excel tool now to practice using our ANOVA test and interpreting the results. We considered the effect that education level, which is variable number 5, and has 3 categories, B, A, M, and D, has on mean spending. Spending is variable number 3. The worksheet tab ANOVA has our results. First of all, we could see that our F test statistic is only 1.569. The F distribution is skewed to the right because it's based on squares. Further, it has 2 degrees of freedom, one for the numerator and one for the denominator. So we would say that F for 2,106 degrees of freedom equals only 1.569 with a p-value of 0.2131. Our null hypothesis is simply equal means. Here, clearly, we cannot reject the null hypothesis. Remember, as always, when the p-value is less than alpha, often 5%, we reject the null. Here our p-value is well greater than alpha, so we can't reject the null. We can also see in our group mean confidence intervals, we get a different estimate of population mean spending for each of the groups. If there were a statistically significant difference in mean spending between our groups B, A, M, and D, the estimate of spending for each group should be different. Here we can see overlap or common range. This frequently happens when our p-value is over 5%. And the higher the p-value, the more common range we would expect. Let's look at another example to practice using our ANOVA method and interpreting the results. Is there a statistically significant difference in mean spending between the marital status groups S, M, and D? Again, we're using alpha equal to 5%. We'd further like to know the specific group mean differences, if any. We begin with our familiar step 1, formulating null and alternative hypotheses. This is easy for ANOVA because it always has the same null, equal population means. If we can reject that null hypothesis, we know only that there's some difference between the population means, but we certainly don't know what that specific difference is. Let's go to our Excel tool to get some results. Our ANOVA tool for variable number 8, independent variable, we would need to add 3 categories, S, M, and D. And our dependent variable number 3 is spending. Clicking the Worksheet tab ANOVA, we can see our results. First, our F statistic is a very strong 10.45, which gives us a p-value very close to 0. We could write our results like this. F for 2,106 degrees of freedom is 10.447 and p is 0.0001. Our degrees of freedom are in the column marked DF. Here we could see that our p-value is not only less than the required 0.05 or 5% alpha. Here we could see that it's less than 1%. So our decision is not only to reject the null, but here we can strongly reject the null. In other words, there's a highly significant mean difference between the groups. Remember, the lower the p-value, the stronger the result, and the more certain we are of our conclusion. However, we still don't know what group spends the most, the least, and if all 3 groups are different. Our group mean confidence intervals will answer that. We can see that the S group goes up to about 3862. The lower limit for both M and D both are greater than that upper limit of 3862. So first of all, we can conclude that the S group spends significantly less than both M and D. Notably, we can see that M and D have a lot of common range or overlap between the intervals. So though S spends significantly less than M and D, there's no significant difference in spending between the M and D groups.